which test do you use to find the radius of convergence?
The ratio test.
The ratio test.
Wow.
And remember, when you compute the ratio, the limit of the ratio with the ratio test, in order to show convergence, when you compute the limit of the ratio test, you want the number to be, you want it to relate to 1 in what way? Actually, it's the other way. If you want convergence, you want the limit of that ratio to be less than 1. Okay? So if you're thinking, yeah, I watched the intro video and I kind of knew what I was doing before when I watched it, but now I've forgotten, start off with the ratio test. And you want the ratio test to be less than 1 in order to get a converging.
Wasn't it in the example you did on the intro video, it was like x plus 3 is less than 4?
Yes.
What does that mean? What does that mean for that ratio test? That was the
She is here.
Good job.
that was
She
the
got this morning.
So,
I was like, my confirmation, you know what? I got that 3 in the morning.
I know what the center point was, but
Never mind.
it was
Yeah, so the radius of convergence for that was 4.
it was 4. So what does that mean?
Okay, so what we're looking at, hello. What we're looking at here, what that means, Jack, is so I've used the word radius of convergence before to refer to. I'll just draw a graph for you. So let's say your centering point is 3, and let's say that the actual graph of whatever function is generating this, we don't know what that function is necessarily. We probably don't know it all, but let's say that function does this. So this right here, this is the real function, and we are trying to approximate that function with this Taylor polynomial, Maclaurin polynomial. It'd be a Taylor because it's centered at 3, right? Okay. So let's say you did, I don't know, let's just make something up here. Let's say you did like a 4-termed polynomial. Maybe that 4-term polynomial would look like this. Something like that, right? You've seen this before. Well, let's say we added a term or 2. Let's say now it's like 5 or 6 terms. Well, now maybe it would be something like this, where it's starting to look really good. Remember how we did all that zooming in before? Right, zoom, 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 and we found barely an error. Well, the more terms you add, the better your approximation gets, right? And so what we found with certain functions, namely sine, cosine, e, and some of these others, that the more terms we added, not only did it seem to get better, but this interval where the blue graph and the red graph seemed to be the same, it widened out. Like if you had 2 terms, and check out the screen. If you had 2 terms, maybe the interval of convergence appeared to be that. Well, if you had 4 terms, maybe it appeared to widen out to be about this. So this radius of convergence would be this distance from the centering point out there to where it looks like things are starting to break apart, right? They're starting to diverge.
Is the radius convergence anywhere within that interval? It's the exact same.
No. Well, so let me come around to that here in a second. Whoa.
Or is it within a certain amount of error?
Hang on one second. So the idea with power series now is this fundamental concept. What if instead of having a partial sum of 6 or 8 or 10 or 20 or 50 terms, what if we made the number of terms head towards infinity? Then what happens, right? So then what we found with sine or cosine, like I mentioned, is that as we increase the number of terms, that interval of convergence seemed to get better and better and better, right? So, it seemed like, I don't know what kind of graph this is. Maybe it is related to sine or cosine. But it seemed like when we were zoomed out to a certain level that it seemed to perfectly converge. Now, here's the truth of the matter. If you stop your Taylor polynomial at a finite number of terms, maybe that number of terms is 20. Maybe it's 20 billion. I don't know. But if you stop somewhere and say, all right, I'm going to use the first 20 billion terms, there will be error everywhere except at the centering point. There will be error everywhere. However, if you say, well, let's let the number of terms approach infinity. So as the number of terms approaches infinity, this polynomial, this Taylor polynomial, would exactly represent this function, sine, cosine, e to the x, whatever it happens to be. It would exactly represent it, not just at the centering point, but everywhere along the interval of convergence. So maybe you remember from last time, we saw this graph specifically. And so this is going to be a little bit of a different graph. It looked like this. There was a vertical asymptote, and then it did this right here. This is a graph of right? Or sorry, graph of this. Okay, so then remember what we did last time is we started adding terms, and it was like, at first it was, we had something like this, and then it was, like this, and then it was like this, and we kept on adding more and more terms. Remember how I said that there seemed to be some kind of a limiting issue there where, I think we got like 10 or 11 or 12 terms in there, but it didn't seem to be growing in its convergence very quickly. And so here's what we're basically trying to do here. We're trying to find this concept, or this interval essentially is, if the number of terms approaches infinity, for what interval will my polynomial exactly represent my function? So for sine and cosine, if we just make the number of terms approach infinity, well then our Taylor polynomial is a perfect representation of sine or cosine. So that would have like an unlimited.
Because the ratio test gives you less than 1?
Well, so in the case of sine and cosine, the ratio test actually gives you 0,
Okay.
which is less than 1, right? But in other cases, it'll give you a number that's less than 1, but not 0. So that was the case here with this one. So with this one in the intro video, so it would be, I'll just do it real quick. So it'd be n plus 1, x plus 3 to the n plus 1, over 4 to the n plus 1 times all this and this, like so. And we want this to be less than 1, right? Because we're looking for convergence. If I think about it like this, if I made that number greater, if I made this greater than 1, then wouldn't I be looking for the interval of divergence? Which is not what I'm really looking for. You might be able to, use it backwards and find what the interval of convergence is, but I'm looking for convergence, so I'm just going to say that's less than 1. So you saw this. So let's see here. If you do all your simplifying, I'm just doing this really quick. This would be what, n plus 1 over n, and it would be x plus 3 to the first, and it would be over 4 like so. I canceled all my plus ones and all that stuff. And then you can apply this limit to both. So it'd be limit of this times limit of this. And so this right here is 1. So that would give you just this, of course, and of course there's no n anymore.
Right. Isn't it also absolute value?
Yeah. It doesn't really matter because n is starting at 0 and going towards infinity, so there's no negatives to even worry about here anyhow. And I've already eliminated the alternating element with the absolute value. So I'm just going really, really fast here because this is all done in the intro video. My point is this, is that you end up with absolute value of x plus 3 is less than, well, over 4 is less than 1, so you get this absolute value of x plus 3 is less than 4. So what this is saying is, remember Remember how we started off? We started off with like an assumption of we're looking for convergence. So everything that follows is going to give you information about convergence, right? So this series converges as long as the absolute value of x plus 3 is less than 4. So check this out. Where do I have room? I'll come down here. I'll come all the way over here, how about? Okay, so do you remember how to solve absolute values?
It's two equations.
Two equations. So it'd be x plus 3 is less than 4, x plus 3 is greater than negative 4.
Yes.
So that would give you, boy, I wrote that in a terrible spot. There we go. Okay, so that would give you x is less than 1 and x is greater than negative 7. So what we're going to find out in a little bit, and I'm going way past, these would be the endpoints of my interval of convergence. What number is exactly in the middle of 1 and negative 7? Negative 3. Centering point, negative 3. So I'm going to come back up here. So here's negative 3. Here's negative 7. Here's 1. So this Taylor polynomial will exactly represent its function, whatever generated it, from negative 7 to 1. We haven't decided about what's happening at the endpoints yet. We don't know if the convergence goes all the way up to the endpoints and includes them, or doesn't include them, or maybe it includes one but not the other, like that kind of thing. We'll look at how to deal with those endpoints in a little bit. But all I found here is for what interval will my Taylor polynomial, if given an infinite number of terms, exactly represent the function that it came from. Okay. All right. Other thoughts or questions there? All right. Well, let's see if you did something with number 2. Let's look at number 2. Number 2 obviously is a little simpler looking. By any chance, does anybody recognize what number 2 is? Looking at that nth term? It's e to the x, yes. Remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. This is actually e. So let's see for what interval, or for what radius of convergence this matches e. Exactly. So here we go. I would say limit as n goes towards infinity of my ratio test. So this would be x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Now remember, I'm looking for convergence. And so what does this have to do if I'm going to have a converging series? It's got to be less than 1. So I'm setting myself up for success. I'm saying I'm looking for convergence. Therefore, that had better be less than 1. A little bit of canceling that can be done. Limit as n goes towards infinity of, oh gosh, it would just be what? X over n plus 1? Okay. So this is where this limit gets interesting. Remember, its limit is n goes towards infinity. It's not x or y or just whatever we want it to be. So think this over. X is going to just be some number, right? Some real number. And n plus 1 is getting gigantic, right? So if the numerator is just some number, we don't know exactly what it is, but it's finite, and the denominator is getting infinitely large, what's the answer to this limit? 0. So in other words, it doesn't really matter what x is. 0 will always be less than 1, right? So what we can then say is, therefore, the radius of convergence is infinite. Because it doesn't matter which x you plug in. Now, on the one that Jack wanted me to go back over, the x mattered, right? Because it ended up being absolute value of x plus 3 has to be less than 4. So, in other words, the radius of convergence very much depends on what the x is, because if x is a certain number, say like 10, 10 plus 3 is not less than 4, right?
So, is it basically, if we had gotten 1/4 is less than 1?
For which one are we talking
For
about?
this one. Just say that, is this, so for
Oh, sure.
anything that's, any number that's between 0 and 1, not
So,
including 1.
if we don't end up getting a 0, there should be some x left over in there.
So, if we do get like 1/4,
It'd be like x is less than 1/4.
well, I'm saying, would it ever be like 1/4 is less than 1?
If it was, then again, the radius would be infinite, right?
That's, okay.
Because if you don't end up with an x on the left side, that means the radius of convergence doesn't depend on x at all, right? In other words, you can plug in whatever x you want, and 1/4 is always less than 1.
Right.
So, yeah, that would work too. Yeah. Okay. So nice comparison between 1 and 2 there. I think there's one more, right? Number 3 for a radius of convergence. Why don't you guys look at number 3 if you haven't already? And then we'll get into intervals of convergence.
Should we just treat x as a constant?
Not necessarily as a constant, but just like any finite number.
Yeah.
You know, it might be 1,000,000, it might be negative, 32, or, it's just some number. But it's the n that's heading towards infinity. Because you can't, the idea here is you can't, like x would be, so like, obviously with number 3, right? The centering point is up there. What would you say the centering point is?
8.
It's 8, that's right. And so then what you would do with this, like let's say we wrote this power series out, we wrote a bunch of terms, we're going to try to do something with it. What you would do is you would plug some number in for x. You'd say, well, what's going on at 8.1? What's happening at 7.999 or something like that? And so that number going in for x would not be infinity. It would just be some number that you're trying to evaluate. But then, like I said, we know that n is headed towards infinity, which would overpower whatever x ends up being. So,
Yeah, I got you.
so you do sort of treat it like it is a constant, but it is still a variable. We just know kind of the bounds of that variable. We know it can't be infinity or negative infinity, I
And
guess.
then if it's greater than 1,
Oh, what happens if you end up something greater than 1
then it's only convergent at C.
at the centering point? That's right. Yes, remember from the video, like a power series will converge either for all real numbers at the centering point or over some finite interval. So I guess you guys hear you guys say that that we might play Rock Canyon in the second round. Is that boys or girls?
Boys, for basketball?
For basketball.
None of the seniors are out of here. I'm
Yeah.
in the senior retreat.
No, they go play.
But yeah,
But like for the basketball game.
yeah, we don't get to go to it. Yeah.
But weren't these guys talking about still wanting to go? Or they were going to try to work some?
No, I talked to the deans today and said that they're not changing their trip.
Okay.
I don't know.
Not even for Meg Bodie?
I might get to go because we just have to dance. It's very
Mhm.
important.
Well,
It's important.
That's so nice, I wish.
I loved how you just you insisted on pronouncing those T's at the end.
Very
important.
important. I don't know. how to do
You know, yeah, they probably could not play the game without that.
it. No, they couldn't.
Um,
They absolutely
basically as important as the ball,
couldn't. Oh my god. Yeah.
right? Without the ball, you just can't play.
Yeah, like they need us there.
It all makes sense.
Therefore, I get to miss part of the senior retreat.
It all makes sense.
For a club.
And then get like all the money for it.
This doesn't
I
make
know that we're
sense
like
to me.
this team in our club, but like required to go.
Mr. Anderson,
Yes, ma'am.
So,
explain yourself.
What's that?
Explain.
Oh, this one?
Yes.
Sure. Okay, so I'm going to just ignore the negative 1 to the n because I'm doing the absolute value per the ratio test. So this would be x minus 8 to the n plus 1 over, if I plug in an n plus 1 for the n, it's really 3n plus 3 plus 1. So you could do like 3n plus 4, I guess, times 3n plus 1 over x minus 8 to the n. So that's the ratio test. And remember, we are looking for the interval, or in this case, the radius of convergence. So we want to make sure that this value is less than 1. So I'm going to put less than 1 right here. And I'm going to get busy doing some simplifying. The only thing I can see that we could really simplify here would be the x minus 8 exponents, right? So I'm going to go limit as n heads towards infinity. And it would be x minus 8 times 3n plus 1 over 3n plus 4 is less than 1. That make sense? Okay, so remember that with a limit of a product, what you can do, as long as the limits exist, you can do the product of the limits. So I think I'll rewrite this a little bit by putting limit as n goes towards infinity of x minus 8 times the limit as n goes towards infinity of 3n plus 1 over 3n plus 4, and all that is supposed to be less than 1. So what is the limit of the right factor, the one on the right?
1.
Yeah, 3 over 3, right? If you do the pre-calc trick, you could do L'Hopital's rule. You could just do it in your head. I'm okay with that. But then what's the limit as n goes towards infinity of that?
X minus 8.
Yeah, there's no n for the limit to do anything to. So this would just end up being, oh, come on, reconnect. You can do it. So it just ends up being x minus 8 is less than 1.
Yes.
Oh, come on, computer. Absolute value, technically, here. Sorry, Phil. Oh. Hey, look at that. It still works. So you end up with absolute value, x minus 8, is less than 1. So this is where I would stop. Here's what I want you to look at this and think, this right here, this is my radius of convergence. It's saying some number minus 8, the absolute value of that has to be less than 1. So let's think about the numbers that work here. Does 8.5 work?
Yeah.
Sure it does. How about 7.2? What about 9.3?
No.
Right, because 9.3 minus 8 is 1.3, and the absolute value of that is 1.3, and that is not less than 1. So it's got to be between 7 and 9. And if the centering point, that's right, Sam. So you don't have to do this for this question. Got to be between 7 and 9. The centering point is 8, so the radius is 1. So right here, this is your radius. You could also look at that and say that that's my radius. They're both 1, obviously. So from centering point to the outer end, obviously it gives you a radius, either end, right? Whether you go center point right or center point left, that would give you your radius. And you can really see that right here. Once you get the x expression totally isolated, like the absolute value of x minus whatever, x plus whatever, that number on the right side, that's your radius.
If we tried to graph,
If we tried to graph what? Okay. I just wasn't sure which graph you're getting at. So just again, a little foreshadowing. What we're going to do next here is we're going to say, great, my radius of convergence is 1. So like what Sam just said is right on the money, going from 7 to 9. The question we're going to try to answer is, what on earth is happening there and there? Does this convergence go up to and include either one or both of the endpoints, or maybe it's neither? Make sense? Okay. Here we go. Let's take a look at number 4. Okay, so, yep. If you're the type of person that writes in like 3-inch tall numbers and letters, let's downsize a little bit for this one. You're going to want to get plenty of information in here. Okay, so I put a note here. Ratio test will easily allow us to find the radius of convergence. But we got to check the endpoints if directed to find this interval of convergence. And I think you'll find some interesting things that happen here. So maybe some unexpected things. Okay, so first step is we got to find the radius. So let me charge you guys with that for number 4, because we just did 2.5 examples of that. So will you please find the radius of convergence for number 4 first? Same thing we've been doing. Leave some room for some other analysis. Do not take up the whole space with this part. Really goes back to day 1 of this when I tried to mess with you with graphs, and we were trying to build out the Taylor polynomial, kept on widening out that interval of convergence. What we're basically doing today is finding how wide could that interval of convergence go, right? Is it limited, or does it just keep getting larger and larger, or is it only going to work at a single point? Anybody coming up with a radius of convergence? Is it infinite? Is it 0? Is it a number? What do you come up with?
It's X.
Well, the radius of
X times
radius
zero.
convergence either has to be infinity, 0, or some number. 1. You guys say 1? Let's find out. So I'm going to do my limit of my ratio here. So it'll be limit as n goes towards infinity of, so it'd be x to the n plus 1 over n plus 1 times n over x to the n. And remember, we're looking for convergence, and so if we are going to get convergence, then that has to be what? It's got to be less than 1. So I'll put, this needs to be less than 1. Basically, I'm drawing my line in the sand saying that I'm looking for convergence. So from here on out, everything is going to be geared towards that. Simplifying wise, the x's simplify a little bit. So it'd be limit as n goes towards infinity, and it would be, I'll write it like this, x times n over n plus 1. What would this end up being if I apply that limit to both and do all the multiplication?
Absolute value of X is
Yep.
less than 1.
That's right, just absolute value of x on the left side is less than 1. There are some steps in between that I showed on the other ones. Are you okay with that? Okay, so once you get the absolute value of whatever blah, 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 x isolated, then the number that's less than, that's the radius of convergence. So I agree, those of you that said radius of convergence is 1, I agree with you. So, I will put radius of convergence is 1. Notice, though, this asks for the interval of convergence. So what I'm going to do is I'm going to come over here and I'm going to say I'm looking for my interval of convergence, and I'm going to say provisionally it's going to be from -1 to 1. I'm going to put little question marks above those because I don't know if there might be an or equal to in there. There may or may not be. So that's my provisional interval of convergence. And I know that it goes from -1 to 1. Do you guys know why I picked those numbers?
That is, you take the centering point,
And how do I know what the centering point is, or what is the centering point? 0. And then what do I do with the rest of it to get that interval?
take the radius, and you go
Plus 1
left.
minus 1.
+1, -1. Yeah, left 1, right 1, and you've got those endpoints, right? Okay, so here's what I need to do. I need to test out the endpoints and see if I get convergence all the way up to and including those endpoints, or perhaps maybe not including them. So here we go. I'll write it like this. I'm going to test x equals -1. So here's what I do. I'm going to go back to my original nth term representation, and I'm going to write, so if x equals -1, this would be sigma from n equals 1 to infinity, and it would be -1 to the n over n. So, it's my great hope that at this point you would look at that series and say, I know what that is. It's alternating. It's an alternating harmonic, right? Like 1 over n is just a harmonic, right? A regular harmonic. But you throw that -1 to the n. Now it's alternating and harmonic. What do we know about an alternating harmonic?
Converge.
So here we go. We say this series is an alternating harmonic. Therefore, it converges. And what that means is my final answer, I know for sure, is going to be -1 is less than or equal to x, because I got convergence at the left endpoint. I still don't know about the right endpoint. I got to do some analysis on that. But I know for sure that the left endpoint, I get convergence all the way up to it and including it. So all I got to do now is test the other one in a similar way. So testing x equals 1. I get sigma from 1 to infinity of 1 to the n over n. Tell me about that one.
It's a regular harmonic.
It's a regular harmonic, which always, that's right. So I'm going to say is a harmonic.
Or a geo. Never mind.
Therefore, no, you're good. Therefore, it diverges. Therefore, my final answer would actually just be right there in the red box. I would get a converging behavior on the left endpoint, diverging behavior on the right endpoint. So this one happened to be a mix. Sometimes they'll both be open, sometimes they'll both be closed, and sometimes it's a mix. You never know. Okay. What do y'all think? Questions?
What do you call this type of notation? Oh, I'm sorry. That notation right there? with the-
Interval?
It's interval notation. Is that what you call it?
That's totally fine.
I couldn't remember.
Yeah, just make sure, the only issue there is make sure your bracket is like really a bracket. Because, like having seen AP tests, people will be like, -1 to 1, and it'll be kind of like, and like, sort of like this hybridy weird thing, like hoping you'll just read what you want to read.
Nice.
Like that kind of thing. So, like, if you're going to do that, like, do it for real. Like, make sure it's, actual hard edged bracket or a very smooth parentheses. So just be careful with your notation there. I would not think that any of you guys would try to, hedge your bets on that and be like, oh, yeah, that was a pretty sharp point there. If you use the less than, all that stuff, no, there's no question. I don't think. I don't know.
I would never.
No, of course not. I'm speaking about other people. Okay. Yeah, and whole other schools, and yeah, no one would. Peyton, no way. What about you, Sam? Would you? No way.
It depends on the mood.
Mood. Okay, so it's a moodiness issue.
Yeah.
Okay. Why don't you guys try? Hopefully you're in a good mood for number 5. Well, let's find out. Okay. So please try number 5.
Yeah.
Find the interval of convergence. So again, this is just like number 4. What you're going to do is find the radius of convergence first. That'll generate some lovely endpoints. And then you test those endpoints out to see if you get convergence or divergence at those endpoints. So this is a lot of good practice with the ratio test over and over and over.
This is kind of a trippy series.
It is a little bit. You guys get a radius of 2?
Yeah.
Okay.
Yeah.
It's a good place to be.
Oh my god, we get 0 to infinity. Isn't that-
0 to the infinitieth.
Isn't that a thing that we can't do?
Thing. So the only way you get 0 to the infinitieth, I think, is if you plug the centering point in.
No.
So your centering point is -1.
-1.
That's what I got. I got the center point as -1. Oh,
Yeah, center
I'm
point's
so
-1.
dumb.
Because it's x plus 1, right?
So it's
So if your radius is 2 and your centering point's at -1, it would be -3 to +1. Remember those same principles that you learned about polynomials, like parabolas and all that? The graphing principles of like a +1 on the inside is actually a left shift. All those principles still apply. I know sometimes it's tempting to think that it's different because it's calculus and power series, but really all these things are polynomials, right? They're really complicated polynomials, but that's all they are, just polynomials.
Is negative one to the n times negative one to the n just one?
So let's think it over. When you multiply like bases, you add your exponents, right? So this would be -1 to the n plus n, or 2n. And then what you could do is you could actually take this and say if you're multiplying exponents, you're actually doing a power to, or a base to a power to a power. So this could be rewritten as -1 squared to the n.
Oh, so it'll just be one.
So it would be 1 to the n. So that's the long answer, yes. I just wanted you to see the way, but your idea was right.
So an alternating series with geometric work. So there's a geometric series where r equals 1.
R is exactly 1.
Yeah. Then, or two, it's 2 over 2.
Negative
Ours
2
is-
over 2, but
But
absolute value.
yeah, absolute value makes it just 1. So
Conversion.
even if it's alternating, that would be diverging, right?
Correct, yeah, the nth term
It's
test.
just
Exactly, that's exactly right. It'd be 1 over, 1 under, 1 over, 1. So the nth term test wouldn't give you a 0. It would give you something that's not a 0, so diverge.
does that make almost like a sine graph?
Well, if you tried to connect the dots with a nice smooth curve, sure, you could make it turn into that.
That's fine.
Yeah, you could try to, I mean, I don't think that that's exactly what it is, but it's that same periodic motion,
Yeah.
up and down, up and down, up and down, yeah,
And yeah.
forever,
Cool.
yeah. I'm going to start my ratio test here. So that's where I'd start. We're looking for an interval of convergence, so we want our ratio test to be less than 1. So I'm looking around. Okay, Peyton is just wrapping it up. Logan
I'm basically
is
there.
wrapping it up, yeah. Sam has reached some kind of stopping point.
Yeah, I don't know.
Have you guys reached stopping point, kind
I
of?
have my answer.
Okay, that's great.
Right.
That's great.
I have an answer.
All right. So let's see here. Let's get a radius of convergence here first. So we got, what, x plus 1 times 2 to the n. Or sorry, it would just be times 2. Yeah. How about over 2? There we go. I'm stumbling and bumbling over my words today. So let's see here. There's no n left, right? So I think it would be absolute value of x plus 1 is less than 2. So my centering point is -1. My radius is 2. And so I would say that my interval of convergence, at least my provisional, is going to be -1 is less than x, which is less than 3. And I'll put those little question marks over those.
You did it wrong. That's what I did the first time. It's
Oh.
-3 to 1.
Oh, goodness gracious. Start over. Why are you clapping? I don't clap when you mess things up. That makes me sad.
Right, that means we did something right.
Good.
Mr. Anderson, every time he's grading our tests, you got it wrong.
No, it's actually the exact opposite. Like, sometimes we'll cheer out loud when you get it right. I really do.
We actually got that.
I want you to do well. And then when you like, when your work goes,
Anderson's so quiet when he grades my test.
so when your so when your work goes, no, that's not true. Because when your work goes like correct, boneheaded mistake that we all make sometimes, I'm like, come on. That's usually my reaction. So if I'm quiet, I don't know what that means. Usually there's some kind of reaction. Usually it's great job, or come on, 5 plus 3 is not 53, that kind of thing.
excited because we got it right. We actually did it right.
Yeah, I usually get excited too. So, all right, good. So that's weird because I just got done talking to Jack about that and then I messed it up myself.
No, we weren't
How about that?
upset with you. We're excited for ourselves.
Good. I'm excited for you too.
This is
So you're okay with this interval then? -3 to 1? I'll try. Maybe I should record myself grading your test, Sam. You can hear. Come on, Sam. Or good job, Sam. You did it.
No, there will be no good job.
There will be no.
Hey, you got the question right.
I think it's a good job in this class.
Multiple choice.
Jack.
All right, so we're going to test the left endpoint. So testing x equals -3. So let's see here. These can definitely get interesting. So it'll be sigma from n equals 0 to infinity. And I've got the -1 to the n hanging out in there. And then I plug in that -3. So -3 plus 1 is -2. So it'd be -2 to the n all over 2 to the n. Well, maybe we should do some simplifying first, right? There's plenty of things going on here. So, say again, Sam?
I think I figured it out for myself.
You think you figured it out?
Yeah, I don't know though.
So, what do y'all think? What do y'all think this is right here? If we simplify that down,
-1.
it's
That's geometric, and it's just 1 if you take away the alternating.
Well, I'm just looking at the yellow highlighted part.
Yeah, because it'd be alternating.
But wouldn't it be a -2 over a +2 to the n? Here, I'll draw in a little. So I'm thinking this would be -2 over +2 all to the n.
Yeah, geometric.
So it'd be -1 to the n, right?
Yes.
And that's something you were just talking about, like
Yeah.
this thing. So then what is -1 to the n times -1 to the n?
It's 1.
1. Right?
Uh-huh.
It'd be 1 to the n. So does this converge or diverge? Why? There we go. Diverges. I'll just put nth term test. Or you could even put doesn't equal 0.
Oh, yeah, because the one to the end we talked about.
Yep.
Yeah.
Okay, so that means on the left endpoint, it's open, right? There's no convergence for the left endpoint. Well, let's test out the other one, the 1. So this would be sigma from n equals 0 to infinity. It'd be -1 to the n times 2 to the n. Over 2 to the n. What happens here?
Same thing. It's just
Essentially the same thing, except instead of 1 to the n, it's -1 to the n, right? Because these two would cancel out to be a 1. So it's just going to just jump back and forth, staying 1 away from the x-axis the whole time. So this would be the same kind of reasoning, right? It'd be diverges because of the nth term test.
Well, I have a question. Wouldn't it, depending on where you started, like if you really thought about it, like that series either, depending on where you end it, that series either equals 0, -1, or 1.
Depending on where you say that again?
Depending, because since it's always going to be -1 + 1 -1 + 1 -1 +1 -1 + 1. That series, depending on if you started it at -1 or at 1, would have to either equal 0, -1, or 1.
But what about all the fractions?
Fractions.
Like between -3, is that what you're talking about? Like numbers you could plug in for x?
No,
No.
I'm talking about.
Oh, you're talking about what the interval of convergence would be?
No, I'm talking about n equals 0 to infinity of -1 to the n.
Right?
It converges to 3, it can converge to 3 different numbers.
Converge to 3 different numbers? Depending on where you start the n?
I understand where he, what I.
I think I know.
It doesn't approach about.
But at an infinite value, it doesn't approach anything.
I understand what you're saying, Jack.
So you're
but
just
you
saying-
will
so-
always be adding or subtracting one. It won't ever like end at a specific.
Right,
value.
and that's kind of the point with the nth term test, right? We don't know like where it ends because it's going to either be at like -1 or 1. How would the 0 happen?
Because started at one,
Start what at one?
you start n equals, you started at n equals 0, right? Plug in 0, start at 1.
You never stop adding, so.
I don't see how you could get a 0.
Just think.
I can see the -1 and the 1 for
I
sure.
understand
what
like
you're
where
saying.
you're coming from, but
But
like,
infinite implies that you don't stop, so.
that you can't put an equal sign.
Oh, I see, like, you're saying a partial sum.
Well, no,
Yes.
I can write it up.
No, I think I know what you're talking about, like a partial sum.
Like you and I were talking about
Yeah.
like sine and cosine graphs,
Sure.
so it's like always.
Yeah, no, I think I get that. But that's not what a power series is, right? The power series goes on forever.
Yeah.
Forever and ever.
Yeah. Right. So 0, 1, right,
If you do this, you
yep.
can say that these all equal 0. So then all you're left with is 1. But if you started,
But you can start the other one,
started at a -1,
right?
you can do the same thing, right?
Yep. Yeah, for sure.
And you can do that forever.
So I'm confused.
Oh, I see, I know.
So what are you confused about?
So this sum equals 1, depending on where you put your parentheses, this one equals 1.
Because
This one equals -1. And if you put your parentheses like this,
some which you can get 1, -1, or 0.
Yeah.
And that's why infinite.
you do it like
Reason
this,
this one is because that'd be -1 plus 0.
Yeah.
then you get 0.
So there's a little, well, it's not little known, there's a, at least in high school, there's a little known idea that an alternating series can be grouped and rearranged to get many different final sums if it converges. So we're talking about something that diverges here, but if you have a converging alternating series, you can actually group it to get a final number that's different depending on the ordering in which you add and subtract.
So how does that work? Because like the associative property of addition, like you're adding all the same numbers.
It's a property of an alternating series. This is kind of a bad time to like have a mind-blowing thing like that because class just ended.
Yeah.
But if you're really curious, research it. It's not hard to find. It really isn't.
That can't work because that would
Thanks
be
for explaining.
Thank you.
-1 or -1 or 0 plus 0 to the infinity and 0 to the infinity indeterminate.
Right, it's an indeterminate.
So it would be 1 or -1 or 0
Plus an infinite number of zeros being added up.
Yeah, so you.
Well, this is a diverging series no matter what.
Yeah, so
Right.
that's-
Yeah, it diverges. So I think Jack was just kind of arguing kind of like the minutia of like how do you get there?
Yeah,
But yeah, because it doesn't, like that's kind of the point, is it doesn't stop.
yeah.
Right? If you did stop it at some partial sum, well then you could arrive at like this confusing, well, I thought it was this and you rearranged it, now it's that. Yeah. Yeah, thank you, Jack. Hello.